This project is the modeling of transcranial focused ultrasound propagation using new Apple Silicon computers by Deborah Shinyan-Bola. What is focused ultrasound? Focused ultrasound is a non-invasive neuromodulation treatment and technique used as a therapeutic device. Focused ultrasound occurs when the ultrasonic beams created by the transducer converge, causing the ultrasound wave to concentrate on a specific region of the tissue. The transducer creates the ultrasonic wave because of the piezoelectric effect. The piezoelectric effect is where the electricity is turned into acoustic waves. There are different types of intensities and waves that transcranial focused ultrasound is offered in. There's high-intensity focused ultrasound, moderate-intensity focused ultrasound, and low-intensity focused ultrasound, which all depend on their frequency. There are also different types of waves, such as pulse waves, which are also known as pulse trains, and then there's also continuous waves. In the figure below, on the right, this is the transducer that is used to apply transcranial focused ultrasound on the brain, and there are many just like it. And on the left, this is a demonstration of the transcranial focused ultrasound application and how it looks in the brain. The focused ultrasound tends to be applied through degassed water because water has a similar speed of sound to that of soft tissue. The numerical modeling of transcranial focused ultrasound has allowed for the accurate prediction of what focused ultrasound should look like in the brain. The numerical models that will and have been utilized for the modeling are created using the Rayleigh integral. The Rayleigh integral accurately predicts the acoustic pressure radiated from specific planar surfaces, which tend to be small individual elements on the focused ultrasound transducer. The equations are given below. In the figures below, these are a demonstration of the propagation of transcranial focused ultrasound that predicts the acoustic intensity of this ultrasonic wave with a color scale that allows for the interpretation of the transcranial focused ultrasound concentrations in the different parts of the brain. Acoustic intensity is the concentration of the amount of focused ultrasound wave that reaches certain areas of the brain. These models commence with the acoustic intensity being depicted in water. Then the models move into the propagation of the transcranial focused ultrasound in the brain, which account for the attenuation caused by the skull. This is because the skull creates reflection with the ultrasound beams as well as transmittance. Transmittance is the amount of the ultrasound beam that actually enters the brain and reaches the focal point, while the reflection is the amount that passes through the different interfaces trying to get to the focal point but does not reach the focal point. The numerical models allow for the 3D perspective of the focused ultrasound to be observed in the brain depending on the intensities and the type of wave that is being used. Currently, numerical models of the transcranial focused ultrasound are very accurate and precise in their modeling. The numerical models must use the computer processors, and they must use central processing units and graphical processing units. These are both processors in different computer systems, and they differ very diversely. Graphical processing units, also known as GPU, have a lot of cores. They have from 100 to 1,000 cores, while central processing units, CPUs, only have from 2 to 64. In the figures below, it can be seen that from the left, the graphical processing units have a host, which is a central processing unit, as the CPU must feed its information into the GPU because of the fact that the CPU can perform very complex operations and calculations. These operations are then stored in the constant memory and the texture memory of the GPU. This information is then entered through the shared memory and then goes to the global memory to be returned to the CPU. The CPU system, on the other hand, fetches information of data, then decodes this information to execute the commands, and then stores this output. But they cannot store a lot as they do not have a lot of space, and therefore this is why they need the GPU space. These transfers are very inefficient, which presents us with a problem for the propagation modeling of transcranial focused ultrasound. The transcranial focused ultrasound propagation modeling must go through several system transfers from CPU to GPU, which is inefficient and it lacks adequate amount of storage for complex models. This problem can be solved by a combined CPU and GPU processor that allows for the CPU to perform complex operations and store this information with access to the GPU space. This is where the Apple implementation comes into play. The Apple Silicon computer has an M1 chip that has a combined CPU and GPU processor that allows for the CPU to perform its complex operations with the space that the GPU provides. The goal of this project is to use the Metal Compute library to create a code that allows for the modeling of transcranial focused ultrasound propagations in Apple Silicon computers, and to compare the efficiency and accuracy of newly created models with previous models that use the PyOpenCL. This is done through a multitude of steps. Primarily, CPU to GPU transfers were done to act as a demonstration of how much slower this process takes when transfers are involved. Then, the Riley integral kernel code was implemented to be used for the PyOpenCL library, which is how old models were created. Then the previous codes were used to model the propagations of transcranial focused ultrasound using the PyOpenCL library. Then this is where we came into play. This is our new implementation. Then, the Riley integral kernel code was implemented to be used on the Metal Compute library. This then led to the creation of a metal code that would allow for the usage of modeling. Then, a transcranial focused ultrasound propagation model was created using the metal codes, and it used the same inputs that were utilized for the PyOpenCL model. These two models, the one with PyOpenCL and the one using metal, were compared. And to ensure metal code efficiency, the metal code was tested on a larger transducer. The results are as following. The transducer is the device for the application for transcranial focused ultrasound. They converge the ultrasonic wave to a specific point. In the transducer below, the dimensions are the X, Y, and Z axes, which represent the length, width, and height, respectively. In the diagram under the text, this is the depiction of how the transducer is meant to converge the ultrasonic beam towards a specific focal point in the water, as there will be minimal attenuation. This transducer model acted as a control, as it was used for both the PyOpenCL and the Metal Compute library. Therefore, theoretically, the propagation models should have the same exact thing. The transducer, as shown in the close-up, have small single individual elements, and this enables the ultrasonic beams to reach the focal point with these small individual elements. The pressure signal is unique to this transducer as it has a frequency of 250 kHz, making it a low-intensity focused ultrasound. Pressure signal is important because it is a variable that can be changed depending on the transducer type. This model below is a representation of the pressure signal produced by the transducer for a frequency of 250 kHz. And pressure is on the y-axis and time is on the x. Here is the comparison between the two models. At the first glance, these models appear to be identical as they have their focal points in the exact same spot, from around 37 to 49 millimeters in the dark red on the y-axis. The color bars differ on a very trivial scale, so this may present minor differences, but they will not be significant. The black line on top of the models act to show where the transducer will converge its beams from. To ensure that these models had no significant difference, a formal comparison was done. This was done by creating a model discrepancy, and this model discrepancy has 0 differences throughout most of the model, whilst there are specific points that have 10th to the 1000th of differences, meaning that they are not significant. These tells us that these models are almost identical. But to ensure that the metal code worked adequately, it was implemented on a spatial transducer. The spatial transducer has no central part to it, as shown through the left side of the model spatial acoustic transducer, which means that the beams should come from the left and the right, which is accurate. And since it has a 750 kilohertz frequency, the focal point should be much lower, and which is correct. This is the pressure signal, and it differs quite largely from the other pressure signal because of the fact that this transducer is a spatial transducer, and it has a 700 kilohertz frequency. These are the pressure signals compared. In conclusion, the models of the focused ultrasound propagation perform the same when implemented into the Metal Compute library to be utilized on Apple Silicon computers, meaning that the metal code is versatile but can accommodate to wide ranges of transducers. In the future, the models will cover much larger ranges and allow for the 3D movement of the focused ultrasound application in the brain. This will open up parameters and allow us to change parameters if they cause negative effects or lead to high concentrations on areas that we do not want. The significance of this project is it allows for the better understanding of transcranial focused ultrasound. It creates an implementation that is more readily available on one computer, as you only need an Apple silicone computer, and it identifies possible negative implications of transcranial ultrasound in certain parameters. I would like to thank Dr. Samuel Pichardo for his mentorship, the Hopkins Brain Institute at the University of Calgary, and Dr. Garcia Diaz for all of her help.